In this video, we will formulate a very simple linear optimization model. Consider the example in which a company called Heavenly Pouch Incorporated produces two types of baby carriers, non-reversible and reversible. And these pictures here illustrate the concept. In a non-reversible carrier, both sides of the sling consist of the same solid color, and in the reversible carrier, one side has a pattern and the other side is solid. So the reversible carrier is essentially 2-in-1. This slide contains all the relevant data that we have concerning the two products. For the non-reversible carrier, we have the following information. One non-reversible carrier sells for $23. It requires 2 linear yards of a solid color fabric to manufacture, and it costs $8 to make one of these carriers. Alright, similar data for the reversible carrier are it sells for $35, and it requires 2 linear yards of printed fabric in addition to the 2 linear yards of solid color fabric. See, it requires twice as much of the material, and it requires the printed fabric in addition to the solid color fabric. And it also costs a little more to manufacture per unit, $10 versus $8 for the non-reversible carrier. There are some additional considerations that we need to take into account. The company has 900 linear yards of solid color fabric and 600 linear yards of printed fabrics available for the new carrier collection. Alright, so there are resources that they're going to use to produce this carrier collection, and these resources are limited. Another important thing is that these resources are already available. You don't need to pay for them. Whatever amount we paid to purchase the resources is considered to be a sunk cost, something that we already encountered, and this cannot be undone. We just have to use the available resources in the optimal possible way. Next, we have the manufacturing budget. The company can spend up to $4,000 on manufacturing the carriers. So this is the cash that they have available at hand that they can spend on manufacturing.
In terms of money, we have no money.
Again, the budget is limited to $4,000. Then there are some marketing considerations. The demand is such that all reversible carriers made are projected to sell, whereas at most 350 non-reversible carriers can be sold. So the demand is essentially unlimited given the quantities that they can produce for the reversible carriers, and the demand for non-reversible carriers is not very high. They assume that they cannot sell more than 350 of these. So we need to formulate a mathematical model that would help the company maximize the profit, which is the difference of the revenues and expenses from manufacturing and selling the new carrier collection. Alright, so essentially we have all these resources described in the problem formulation, and we need to build a model that will help us to use these resources in the most efficient fashion. This is a very typical production planning problem, and before we proceed to formulating it, I would like to summarize the major data that we have concerning the problem in a single table, which we can use when we build our model. The way we will typically summarize the data concerning the production planning problems, we will have the columns corresponding to our products, so we'll have 2 columns, and then we'll have the rows corresponding to the resources. So we have non-reversible carrier and then reversible carrier. So these are our products. Here we'll have the price. $23 for non-reversible and $35 for reversible. Then for the resources we have solid color fabrics and we have the printed fabrics. So here I'll have a row for solid fabric. So one non-reversible carrier requires 2 linear yards of solid color fabric. So we put 2 here. And one reversible carrier also requires 2 linear yards of solid color fabric. So 2 here as well. And then here we will use this last column to describe the availability of each resource. Let me call it a limit. So the resources are limited and the limits will be specified in this column. So we have 900 linear yards of solid color fabric available. So here we have 900. And then we have the printed fabric. The printed fabric is not used for non-reversible carriers. So here we have 0. And we use 2 linear yards of printed fabric for reversible carriers. And then we had 600 linear yards of printed fabric available. So this is our limit for this resource. And then we have the manufacturing costs, and the budget that we have for these manufacturing costs constitute our third resource. So let me call it manufacturing here. It costs $8 to manufacture a non-reversible carrier, and it costs $10 to manufacture a reversible carrier, and we had $4,000 as a limit for our manufacturing budget. This summarizes the production or technological process, but then we also had some marketing constraints. We said that we cannot sell more than 350 of non-reversible carriers. So here we will put this as less than or equal to 350 for the marketing considerations. Alright, looking back at the data, we can see that we summarized all the information we had. So now we will use this table when we build our model.
Now, the rest of the plan is simple.
To start building the actual model, we first need to define the decision variables for which we need to figure out what is controlled and what is not controlled by us in this problem. So this table summarizes the data that we have, and these are what we call the parameters of our model, and the parameters is something we cannot control. So this is something that is given to us. But what we can control in this situation is how many units of each type of carriers we will produce. So we have non-reversible carriers, we have reversible carriers, and our plan consists of determining how many units of each we need to produce. Therefore, it is natural to define our decision variables as x1, the number of non-reversible carriers to manufacture, and then x2, the number of reversible carriers to manufacture. When we define our decision variables, it is important to define them in a way that we can express our objective and all of the constraints summarized in this table in terms of these decision variables. And it is easy to see that with our definition of decision variables, we can easily do this. So we'll start by formulating the objective function. The objective in our case is to maximize the profit, which is the revenue minus the cost, and we can easily describe both the revenue and the costs in terms of our decision variables. Since the contribution of each non-reversible carrier to the revenue is $23 and we produce x1 units of non-reversible carriers, the total contribution of non-reversible carriers to the revenue will be 23 times x1, and similarly we have 35 times x2 for the contribution of the reversible carriers. And then this summarizes our revenue, and we need to subtract the costs. The only costs we encounter here would be the manufacturing costs, because remember, the resources that are the solid fabrics and the printed fabrics are already there. We already paid for them before, and the selling price is supposed to reflect the cost of these resources. So this is something that we don't control in this model. The only cost that we encounter would be $8 per unit of non-reversible carriers in manufacturing costs and $10 per unit of reversible carriers in manufacturing costs. This totals to 8 times x1 plus 10 times x2 in manufacturing costs for the whole collection. and we subtract this from the revenue in order to find profit, and we see that our profit now is 15 times x1 plus 25 times x2, so this is going to be our objective. More specifically, we want to choose x1 and x2 values that will maximize this objective function that is given by 15 times x1 plus 25 times x2, and we typically use z to denote the objective function value. So the way we formulate it, we say maximize z equal to 15 times x1 plus 25 times x2, and this variable z is kind of reserved for the objective value in linear optimization. So typically when we say z, by default this means that we are talking about the objective function value. So we maximize our objective function, and sometimes we'll abbreviate this by max, or if you were minimizing, we could abbreviate it by min. So these are some of the notations that we typically use. And the coefficient of an objective function variable is called an objective function coefficient. So we have the objective function coefficient for x1 is 15, and the objective function coefficient for x2 is 25. Again, these are the parameters of our model that are given. It is important to clearly distinguish between the parameters and the variables. The parameters would be the constants that represent the input data for our problem, and the variables would be the decision variables that we define. So then, of course, when you look at this objective, the higher are the values of x1 and x2, the higher is the objective value, so you would want to drive these values to plus infinity, right? But the values of x1 and x2 that they can take are limited by the constraints that we have. So we had 4 different types of constraints mentioned in our problem statement. So we had only 900 linear yards of solid color fabric available. Then we also had the limit on the amount of the printed fabrics that we can use, and we had the limit on the manufacturing budget, as well as this marketing consideration that told us that we cannot sell more than 350 non-reversible carriers. So let's discuss how we can formulate these constraints in terms of our decision variables. So here we have the table with all of our data, and the first constraint is only 900 linear yards of solid color fabrics are available. So the solid color fabric line in our table is given here. So 2 linear yards are used per non-reversible carrier and 2 linear yards are used per reversible carrier. So the overall amount of solid color fabric that we'll use will be 2 times x1 plus 2 times x2, and this overall quantity that we can use is limited by 900 linear yards that we have available. So this is our first constraint. Now the second constraint tells us that at most 600 linear yards of printed fabric can be used. The printed fabric requirements are given in this line of the table. We don't use any printed fabric when we produce non-reversible carriers, and we use 2 linear yards per reversible carrier. So we write the constraint, the overall amount of the printed fabric that we use is given by 2 times x2, and this amount is limited by 600 linear yards that we have available, and this is our second constraint. Then the third constraint says that the manufacturing budget is limited to $4,000. The manufacturing costs per unit of each product are listed in this line right here, so we need $8 of manufacturing budget per unit of non-reversible carrier and $10 per unit of reversible carrier. So the total amount of money that we are going to use for manufacturing will be 8 times x1 plus 10 times x2, and this must be less than or equal to $4,000. So this is our budget constraint. And finally, the constraint 4 is the marketing constraint that tells us that at most 350 non-reversible carriers can be sold. So the number of non-reversible carriers is given by our variable x1. Therefore, x1 is less than or equal to 350, and this is our last constraint. So when we look at the first three constraints, they kind of naturally ask for simplifications, right? Normally there is a benefit in keeping them as they are, because these coefficients here, they represent exactly the quantities of each resource that we use to produce each product, and then the right hand side lists the resource availability. But just to show that we can simplify the constraints, let's divide both sides of the first constraint by 2, then this will give us an equivalent constraint. x1 plus x2 is less than or equal to 450. Then this constraint is equivalent to x2 is less than or equal to 300. And here we can divide both sides by 2 as well. So we'll obtain 4x1 plus 5x2 is less than or equal to 2000. So we simplify this constraint so that all the coefficients are still integer, but the magnitude of the coefficients and right-hand sides is now less for the first three constraints. Alright, so in summary, this is what we have. We call the first constraint the solid color fabric constraint. Then the second one is the printed fabric constraint. The third one is the budget constraint, and the fourth one is the demand constraint. There is some additional terminology that I want to mention before we proceed. The coefficients in the constraints are often called the technological coefficients because they tend to describe the technological process that we use in manufacturing. Then the number on the right hand side of the constraints is called the constraints right hand side naturally, and sometimes it's abbreviated to RHS for right hand side. Finally, when we defined our decision variables, we didn't really specify of what type they are, right? And normally this is an important consideration that we need to address in the very beginning when we define our decision variables. The question that we always need to ask ourselves is, can the decision variables only assume non-negative values, or can they also be negative? In our case, since the decision variables represent the quantities of products to produce, obviously they must be non-negative. You cannot produce a negative number of carriers, right? Therefore, we have the non-negativity constraint for each of the variables. This is something that we need to put in our model usually. And then if the variables can assume both positive and negative values, the decision variable is called unrestricted in sign. Sometimes we abbreviate it to URS, unrestricted in sign, or we just write xi belongs to the set of real numbers R. So in our case, both x1 and x2 are supposed to be non-negative. So we need to add the non-negativity in our model. Moreover, if we go into more detail, the quantities of carriers that we can produce are actually supposed to be integer, because you cannot produce, say, 1/2 of the carrier, right? So to have a more precise model, we should actually put this constraint in the model as well. We should say that x1 and x2 are actually non-negative integers. But in linear programming model, we don't allow the integrality constraints because they make the model a lot more complicated.
But am I upset? No, I am not.
And later on we'll discuss integer programming models and talk about why the problem becomes more difficult when we add the integrality constraint. For this part of the course, when we discuss linear programming, we will assume that fractional values are allowed. So the variables can take fractional values even for the problems where this doesn't really make physical sense. And I want to stress that even when we ignore the integrality constraints, the models that we build in such cases are still useful because, first of all, when we are talking about large quantities of products, then typically for the problem like the one we are looking at here, if let's say we obtain a fractional solution, we can just round down the optimal values for our variables and we will still obtain a very reasonable solution. And typically the data that we use in the models of real life problems are not perfect anyway. So as the famous statistician George Box said, all models are wrong, but some are useful, and this is exactly what we can claim in the case of linear programming models. So we'll talk about this issue in more detail later on, but for now let's just say that we assume that fractional values are allowed for this part of the course. Alright, to summarize, this is the model that we obtained. We have this simple two-variable LP, or linear program as we call it. Why do we call it linear program? Because all the functions involved in this formulation are linear. Let's define what a linear function is more formally. A function of n variables is called linear if it can be represented in the following form. So you have f of x is given by the summation of cj's xj's for j between 1 and n, where cj's would be the constant coefficients and xj's are our decision variables. So if we look at our model here, we can see that all the functions involved in the objective and in the constraints are linear functions. For example, c1 is given by 15 and c2 is given by 25 in our objective function, and c1 is given by 1 and c2 is given by 1 in the first constraint, and so on. So this explains the name linear program or linear optimization problem.